Welcome to Maths with Bob. Today we're looking at logarithms and exponentials. And the first thing we're going to have a look at is, well, what is the definition of a logarithm, I suppose. And you can see here that obviously it's a index, really, of a base. So let's actually have a look. Suppose someone said to you, what is the logarithm of 27 to the base 3? Okay, so the first thing is, okay, what are we taking the logarithm of? Well, okay, we are taking the log of, obviously, that 27. So we're taking the log of 27. Okay. The other important bit of information, obviously, is the base to which we are taking it to, which you can see here is 3. So we're actually taking the logarithm of 27 to the base 3. So what is this asking us? Well, it's asking us, really, what is the power, or if you like, the index of 3 that gives 27. So you could say, if that's equal to, say, x, then you could say something like, okay, 3 to the x is equal to 27. And hopefully we can see that that answer would be 3. Okay, so the answer to that one is 3. How about the logarithm of 9 to the base 3? Okay, hopefully you might be able to see that that is actually 2, right? So you can rewrite these. So you could write this as, okay, 3 cubed equals 27. You could rewrite this one as 3 squared is equal to 9. Okay. So you can see here the answers to the logarithms of numbers are in fact indexes, or if you like, powers of the base to which you take the logarithm 2. Okay. So normally on the calculator we have two logarithms tabulated. There's log and ln. So here I've just put up the calculator buttons concerning logarithms, and you can see here there's one called log and one called in. It may not look like a log button, but it's Logarithm Napierian after John Napier, or sometimes called natural logarithms. So this button here is base 10. Okay, just like the Richter scale, maybe decibels as well. This is actually log to the base e. Okay, so this is, I should say base e perhaps. So this would be like log 10, the base, and then we just pick a number. We type a number into the calculator. So if you put 100, just type in 100 log to the base 10, and you should get 2. Okay. This is actually, it's just right here, this is actually base e. Now, what is e? This is an exponential, okay, the exponential. And it is in fact, irrational, like pi, 2.71828. If you just press e to the power 1 on your calculator, you'll be able to get a correct 10 decimal places, or however many places there are on your calculator. But e is roughly about 2.718, roughly. Okay. Well, do the logs have rules or laws? Yes, you can see here these are the log laws, 1, 2, 3. There's a couple of special ones, 4 and 5. You'll see here I haven't actually written a base in for 1, 2 and 3, because these actually work for any base. LOG on your calculator, as you know, is log to the base 10. But they work, as I said, for any base. So let's do some examples. Okay, let's have a see that what's the log of 6 could be written as what? The log of 2 plus the log of 3. Obviously, say base 10. It actually doesn't matter what base. Let's have a look at 2. So the log of, say, 25 over 2 could be written as the log of 25 minus the log of 2. Let's have a look at the third one. Okay, so the third one, say the log of, say, 5 cubed is equal to 3 lots of the log of 5. Now that will work for any base. If you look at 4 and 5, these are basically the logarithm of a to the base. A is 1. So if the base and the number are the same, then the answer is 1. Okay, the index of the actual base to get the number itself obviously has to be 1. And if you look at 5, the logarithm of 1 to the base a is 0, because any base to the power 0 would be 1. Now right down the bottom there's quite an interesting one called the change of base rule, which is quite useful because, as you know, on the calculator there's only two bases tabulated, base 10 and base e. So if someone said to you, what is the logarithm of 7 to the base 3? Okay, there's no actually button you can use on the calculator directly to evaluate this, but all you do is you just change the base. So you just say that's the log of 7, and now obviously you press the log button on the calculator, which would be base 10. I'll just put it in here, and log of 10 to the base 3. Now, it wouldn't matter, you could use the other base one as well, so you can just take those ln7 if you like on ln3. Okay, and you get the same answer. Okay, so what would it roughly be? Well, 3 to the power 1 is 3. 3 squared is 9, so you can see it's between 1 and 2. So if you just press the log of 7 divided by the log of 3, you can see it's about 1.77, two decimal places, so it's about approximately 1.77 if you write 2 dp. Quite useful, the idea of changing the base of a logarithm. Okay, now let's actually, in a minute, we'll have a look at what do the graphs look like. Now, a lot of times the logs and exponentials are always done together, and if you have a look at GeoGebra, this next one I'll just show you. Okay, here you can see I've drawn in the blue, this is just an ordinary exponential. This is actually, in this case, this is 4 to the x. I'll just put the animation on just to show you. This is 5 to the x, 6 to the x, 7 to the x, 8 to the x, 9 to the x, okay, 10 to the x, okay, then coming back 9 to the x. And you can see the blue one is the exponential and the red one is the actual log graph. So you can see something about the relationship between them if you have a look at this. They are just reflections in the line y equals x. Okay, so at the moment we've got, you can see here the two graphs are just oscillating, well, animating, you might say, with GeoGebra and a slider. I'm actually using the change of base rule to actually plot the logarithm graph from the exponential, actually. Anyway, so this is using the a as the base number. Okay, you can see, obviously, I always say that the logarithms go around the corner, they go zoom, 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 and the exponentials go whoosh. So we always do logs and exponentials together, basically because they're inverse functions, if you like, of each other, reflections, if you like, in the line y equals x. Well, okay, well, let's actually have a quick look at the derivative of the logs, and hence, obviously, the integral as well of the derivative. So, first up is, if it's a log to the base e of some function, then its derivative is just the derivative of that function, f dash x, all over fx. Okay, so what does that mean? So let's just do a quick example. Okay, suppose we had, okay, e.g., so we had y is equal to log to the base e, sometimes written as ln, okay, of say sine of x. Okay. Okay, so what would the derivative of the log of sine of x to the base e be? Okay, well that would be equal to, okay, y dash or dy dx would equal, okay, the derivative of sine, d sine, which is cosine of x, all over this, well, the original function, sine x. Okay, so you can just see here this would be equal to what? Cot x. Sine on cos is tan, and cos on sine, hopefully, is the reciprocal of tan, which is cot. Okay, now, let's actually just do something, and hence, obviously, the integral of cot actually comes back to log sine, but let's actually change the base. Okay, what happens when I change the base? Say it's the log of base 10 of sine x. Okay, well, as it stands, we can't differentiate it. We need to do what's called a change of base. So we need to change it into log to the base e, or ln's. So all you do is you just say, okay, say rewrite that as what? ln, or log to the base e, if you like, of sine x over log to the base e of 10. You can see here there's just that factor on the bottom that's going to be the difference. Okay, so therefore, okay, y dash will be, if you like, the same for the log sine, so it'll be cos on sine, but it'll all be over log 10, so it'll be actually, if you like, I'll just write it as one at the front here. I'll just change it to ln, just change the notation slightly, to ln 10, okay, which is log to the base e of 10, and by cosine x on sine x, okay, I'd have to do the derivative of log of sine of x to the base e as before, okay, put the derivative on top of the original function, and you can see here the only difference is there's going to be cot x, if you like, cot of x all over this, if you like, constant ln 10. Okay, so we'll just go on to, how about we have a look at some integrals as well. Okay, we're now going to look at some integrals. Now, we need to look at basically a fractional, or a rational function, I suppose, which has the derivative of the bottom, fx, on the top, f dash x. So if we had something like, say I wanted to integrate, say for instance, say, let's have a look at the bottom, make it x squared plus, that's supposed to be x squared there, plus 3. The derivative of the bottom, okay, should actually be, what, just 2x, okay? I could put a dx on the top, if you like, or on the side. So this would integrate back up to, let's have a look at that. Obviously, it's going to turn into just ordinary log to the base e. Okay, they all come back to log to the base e of the function, which was x squared plus 3 on the bottom. And obviously, we put the constant of integration in here. Okay, now suppose, actually, let's just change this slightly. Okay, suppose we didn't have the 2 here. Okay, suppose it was just the integral of x over x squared plus 3. Okay, not quite the derivative of the bottom on the top, but just a constant multiplier out. So what you do is all you do is you just say, okay, you put it in, okay, you say, okay, well now it becomes the derivative of the bottom is now on the top. However, I have changed it, so I need to multiply by the fraction, and then I end up just getting a half here. So we just have these constant multipliers, which we can adjust the integral, or integrand if you like, with. Okay, well, we'll just leave it there for the time being. The exponentials will be in the next video. Thank you for watching. Bye for now.